learned that conservative force will relate to a potential energy. So there's a relationship between conservative forces and potential energy. We have this work done by conservative force equal to negative change of potential energy. That is negative of potential final minus potential initial, and we know that. So if we go backwards, if we differentiate, then we have, if we know the potential energy is related to position, then we have du dx negative, it's a negative sign, and equals to fx, because it's just like we want to get this force. What do? We just differentiate. We differentiate this term with differentiate this term, we get the force. So for example, that we have this u of gravitational is related to mg of y, the height, right? So this is y direction. So I'll say the conservative force related to that equals negative d of that u is mgy and d of y, because it's y direction, and that is negative mg. This tells us the force is mg, the direction negative. Negative means it's pointing down. Because why? Because you see the height is y. Obviously when we talk about height, this is y equals to 0. If you are here, isn't that this is height of y? So up is positive, and you have positive gravitational potential energy, but the force on it is negative mg, is opposite direction of that height. Now if we know that potential energy of elastic is 1/2 k of x squared, x is the displacement of the end of a spring, and then we say the force F of elastic related to its negative differential of that over dx, because it's x direction, and then we get a negative of kx. That is the elastic force. Negative means it is always at opposite direction of displacement. If x is positive, elastic force will be negative of direction. So this is a relationship between conservative forces and potential energy. Now let's learn a new concept about stable equilibrium. And this is a mass spring system of spring constant K, and we know that elastic force is, the magnitude is kx. Right now the block has a positive x, and the elastic force is at opposite direction, right? Magnitude is kx. The related potential energy for this conservative force is that elastic potential energy 1/2 kx squared. If we plot the potential energy versus position x, it comes out as this curve. This negative x max means the block goes to the far left. The positive means to go to the far right. And this is a so-called equilibrium position. This is an equilibrium position defined as du of dx equals to 0, which means that potential energy versus position curve, the slope is flat. It's only here is flat. But you see, what if we have a potential energy versus position if it's the other way around? At this point, the slope is also 0. The du dx is also equal to 0, but this is not a stable equilibrium, because if you push this object to the left, and the potential energy is going to drop, and it's not going to come back the other way around too. This is an unstable equilibrium. But what about this one? Because you see, what happened is, if we push to the left, right? Now, push to the left, which means the block goes to the left. But the force, once the spring gets compressed, the force will be opposite direction. So we'll try to push it back. Same thing, if you push the object to the right, the force again will try to pull it back. So this is called elastic restoring force. It's try to bring the object always back to this position. So a stable equilibrium has the character of ux is a minimum, unlike this point is a maximum. Because you see, if we have this one partial du of dx, right? If we do that, that equals to of the force associated with that. And obviously for this side, this slope is positive. So wait a minute, the slope is, for this side, it's negative du dx equal to that force, right? So if you do du dx, the slope is positive, but after negative, then the force is, which means you go to left, your force is also point to the left. So we'll further push you to the left. Let me explain one more time, okay? Look at this one. This one, when you do du dx, the slope is negative. But after time it is negative. This slope, I'm sorry, is positive. After time a negative, the force is negative. That means you go to a negative position, the force is negative, so you will further go negative. But not like this one. Look at this one. You go to left, right? The slope here is negative, isn't it? Because this way. But this is slope. After negative sign, the force is positive. That means the force is this way. The kx force will try to push you back. But what about here? You come here to the right, the slope is a positive. But after time a negative sign, the force is negative. That will try to bring you back. So this is a stable equilibrium. We just talked about the potential energy associated with conservative force. Let's look at this case. This is the potential energy associated with the force between two neutral atoms. The potential energy here varies a unit, which is very small, times 10 to the negative 23 of joule. And roughly here is 5.0. And it looks like a little bit unproportional, and let's mark here is negative 15.0. This is a very interesting curve. Let's take a look. According to what we learned, that the conservative force in this case, let's assume, well, x is the distance, that it's a variable between the two neutral atoms, that f of x equals to negative du dx. And we know that slope of a curve of u versus x, this x varies a unit, also very small, that is 10 to the negative 10 of a meter. So the slope for a u versus x curve actually is du dx. And also we learned that when du dx equals to 0, that is either maximum or minimum. And in this case, we got a minimum, which is right here. Not only so, that from here, we solve that particular x, let's name x naught. The result actually comes out very close to 3.0 of 10 to the negative 10 meters. What does that mean? That means when the distance between two neutral atoms is at 3.0 times 10 to the negative 10 meters, that the force between them is 0. At that time, because du dx equal to force equal to 0. And at that time, because when we plug in this x of O into this equation, we will get, this is so-called the potential energy minimum. Obviously, we can see it's minimum. So this is a, we say, stable equilibrium position. This is equilibrium position. However, if we push, imagine if we push one of the atoms towards the left, which means towards x less than 3.0 of 10 to negative 10 meters. So since this is a stable equilibrium position, we expect that the force the other atom pushes this one will be to the right, because we have atom that we assume have a displacement to the left. If the force is to the right, then this atom will come back to this so-called stable equilibrium position. So let's take a look at what happened. If we look at the slope here, the slope here is negative, obviously. When slope was negative, which is du dx, after you time a negative sign in front of it, the force is positive. Positive means this direction. That is positive x direction. So that is true if somehow the atom is a little bit away from its equilibrium position, and then let's say to the left, and then the force on it to the right. Let's look at here. The slope here is positive, and therefore the force is a negative times that value, that is the force will be, because du dx is slope. Slope is positive, force is negative. Negative means push that way. So if the object, the atom actually goes to on the right side of that equilibrium position, and the force will also push it back to its stable equilibrium position. So this is a very interesting curve. We just learned from chapter 8 that the summation of work done by non-constitutive force equals to delta of mechanical energy. That is, delta of mechanical energy consists of kinetic energy Ke plus potential energy of gravitational plus potential energy of elastic. So as a matter of fact, that delta of Ke plus Ug plus U epsilon actually can be replaced by delta of Ke plus delta of gravitational potential energy and plus delta of elastic potential energy. So this is a very, very useful equation. By using this equation, we can solve a lot of problems, which is very convenient to us. For example, let's assume this slope has no friction with respect to the block placed on the top. Obviously, then the block will slide down. That is very true. Let's say at the end of the slope, we have a spring of spring constant K. Initially, it's that long. And so the distance between the front of the block and the beginning of the spring is distance d. And obviously, with a constant mass m and with a constant angle theta for the slope, without friction, the bigger the d, the bigger the compression to the spring when the block slide down. So let's say later the block actually slide down and stopped here. The maximum compression is x. And obviously this is only momentarily, because the spring gets compressed and the spring will try to push the block up the hill. That's what's going to happen later. So the question is, if we know the maximum compression is x meters, what is the initial distance d? Obviously, x is a function of d. And the bigger the x, the compression, the bigger the initial distance d. We can solve this problem by using Newton's laws, but the problem is when a block hit the spring, because this x initially is variable, the force from the spring is not a constant. By using Newton's second law, sigma F equal to ma, it requires most of the time constant force. So it's not convenient. So what we do is still we need to mark how many forces. We have gravity, mg. We have normal force, Fn, perpendicular to the slope. There's no friction. Well, when the block hit the spring, we will add one more force. And that is, if we draw the picture, when the block comes to here at this position, and there's one more force on the block, which is the kx force. So out of the three force which one is Fn, the other is mg, the other is kx. Only the Fn is non-conductive force. So we say work done by non-conductive force, in this case, the sigma. Actually, we only have one, that is work done by Fn. And that equals to 0 because our displacement is d plus x. It's perpendicular to Fn. So, in this case, if the sigma of work done by non-conductive force equal to 0, then delta ME equal to 0, which means mechanical energy is conserved. There are two ways to solve this problem. If we say mechanical energy of initial equals to mechanical energy of final, if we do that, we have to list the mechanical energy initial, which is at this position, kinetic, which obviously is 0 because initial velocity equals 0, and elastic, obviously 0 because springs have not been compressed yet. And yes, this block has gravitational potential energy, and we can choose a reference level as h equals 0 so we can figure out how high the initial position is. Then we do the similar thing for the final. Final kinetic, because this x is the maximum compression, so the block stops, so final velocity equals 0, kinetic energy is 0. Spring has been compressed by x meters, so there is elastic potential energy. And however, well, the block, whether the block has gravitational potential energy, right, the final position, it really depends on where is h equals 0, the height 0 line. So sometimes we feel it is easier to follow delta KE plus delta UG plus delta U epsilon equal to 0 is easier, instead of list the total initial and total final. So let's take a look. Our delta KE is 0 minus 0 because initial has no speed, final has no speed, plus delta UG. Now delta UG, this is a case that we only need to worry about that initial position, final position. So let's take a look. That as a matter of fact, the displacement is x plus d along the slope. And the slope has an angle of theta. So how much it dropped actually is delta H. Drops means the change of potential energy is negative because it gets lower. So as a matter of fact, the second term is simply negative mg of this delta H. This delta H obviously is the slope x plus d of sine theta. So we get our change of gravitational potential energy term. And then the last term, change of elastic potential, it's very simple. 1/2 kx squared minus 0 because initially there's no compression. Final, we do compress the spring by x meters, so that equals to 0. And let's take a look of this equation. And since that mass is given, g is gravitational constant, d x is given, that's how much it gets compressed, spring constant k is given, angle theta is the angle of slope. So we do have a relationship that d can be expressed by those terms. And what if there is a friction? If there is a friction, we must know mu k. So, and Fk equals to mu k times normal force, Fn. And we need to find a normal force. Because if we look at it, this mg can be split by that mg of cosine. Down the hill is mg of sine theta. So this one is mg of cosine theta. Fn is balanced by mg cosine theta because everything else, the force is along the slope. So that equals to mu k times mg of cosine theta. And once we know that, the kinetic friction does a negative work. So it is negative Fk time displacement because it comes down by this much. Okay. Now this time, because there is a kinetic friction, for the same initial distance d, the x has to be smaller than before, because part of energy is being wasted because of this negative work. Negative work done equals to, because the work done by non-kinetic force is now done by this kinetic friction, equals to change of kinetic, that is 0 minus 0 again, a change of gravitational potential similar, minus mg of x prime plus d of sine theta. And the final elastic is 1/2 k of x prime of square minus 0. That's change of elastic. So from there, and we can certainly replace this to here. From here, we can find that for the same initial distance d, that if with a mu k, such a coefficient kinetic friction, how much the spring will be compressed for the same problem.